Thank you, Chair, for the introduction. I'm Antonio Pallotti, researcher supervisor in technoscience and the lead of the graphology laboratory in the University of Rome San Raffaele. The work that I will show you is an ongoing project, so a preliminary design study in collaboration with the University of Rome for Italico and Department of Management and Law in the University of Rome Tor Vergata. So I leave the floor to the PhD student, Emanuele D'Angelo Antonio.
Good morning to everyone. Thank you, Antonio, for the presentation. I'm D'Angelo Antonio, an industrial PhD student, and today I will show you these works entitled the Wearable System for IoT-based telerehabilitation of patients suffering from respiratory disease or COVID-19. Let's start with a brief introduction about the context in which the project develops. During the last 2 years, 2-3 years more or less, health services around the world have had to deal with the emergency caused by COVID-19. In this period, in order to reduce the infections, hospitals have to interrupt therapies, leaving patients without treatments and without therapies. So to solve this issue, health services developed telemedicine services to follow patients at distance, living there at home. But what is telemedicine? The telemedicine is defined by the World Health Organization as the delivery of healthcare services where patients and providers are separated by distance. And in particular, in the context of COVID-19, telemonitoring and telerehabilitation services were developed for diseases affecting the cardiorespiratory system and to the COVID-19. Naturally, wearable devices and IoT frameworks are key elements in the development of these kind of systems because they need signals and data acquired directly to the patients and then sent to the physician or to the telerehabilitation teams in order to evaluate the effects of the telerehabilitation programs or the telemedicine program on the patients and to evaluate naturally their status. Conventional rehabilitation protocols are based on monitoring some vital parameters, like for example heart rate, temperature, oxygen saturation, but most are based on some motor exercises, like for example respiratory exercises and motor reactivation exercises. Rehabilitation structured in this way was shown very positive effects, like for example reduction in muscle weakness and dyspnea, a better adaptation to muscular effort, and a more or less quick return to activities of daily living. But the conventional rehabilitation protocols are operator independent. This means that the effects of the rehabilitation protocols depends on the intensity of the exercises done by the patients, also where the patients are not in contact with the rehabilitator and so with the rehabilitation team, but they perform the exercises at home. On the other hand, telerehabilitation services are defined by the healthcare system as the remote provision of services intending to enable, restore or improve the psychophysical functioning of people. Using telerehabilitation services, the effects of conventional rehabilitation are preserved, but also some issues are solved, like for example the distance, and naturally the cost-benefit ratio is improved because one rehabilitation team is able to follow more patients at distance using the telerehabilitation services. After that, with the use of wearable sensors and the IoT infrastructures, it is possible to have a real-time monitoring in order to evaluate the adherence to the rehabilitation protocol, so the patients can be followed during the rehabilitation protocol, and also to obtain quantitative parameters that are very useful for the physician to evaluate the rehabilitation process. In this paper, we propose the architecture, framework, and the essential elements of the IoT-based telerehabilitation service, including quantitative movement monitoring based on wearable devices. This study focused on the presentation of the wearable system, and our main contribution consists of a feasibility study performed to assess the minimum number of sensors and the placement of that sensors in order to acquire signals, quantitative signals of the exercises performed. In the following slides, I will show you the wearable system, and we can start with the sensorized shirt that we will be able to acquire the electrical cardiac activity of the patient during the performance of the telerehabilitation exercises. So we can acquire a one-lead ECG signal using a protocentral board with the only with 3 electrodes that are the red dots, so position on the chest near the arms, and one electrode on the ribs. The shirt integrates also a digital thermometer and a 3-axis accelerometer that placed on the ribs is able to acquire signals regarding the respiratory exercises and the respiratory rate to say an important parameter. All these, at the end, also the spark fan, pulse oximeter, and heart rate sensors are placed on the index finger in order to obtain naturally the oxygen saturation and so the heart rate. All the sensors are connected to an Arduino board, in particular the Arduino Miga, and it uses a Bluetooth module for the communication with the acquisition unit. The other wearable devices are 2 sensorized socks, in particular the 16 socks that integrate 4 force sensors under the foot sole, and a Mimio sensor placed a few centimeters above the malleolus. All the sensors are connected in this case with another Arduino board, that is the Arduino Nano BLE Sense, that integrates a low energy Bluetooth module for the communication with the acquisition unit. At the end, we have also developed a sensorized belt that integrates an Arduino Nano BLE Sense with a 9-axis Mimio. And this sensor placed in this region on the pelvis is very important to monitor, to assess the balance and the motion of the patient. The transmission unit is composed by a mobile application that is developed using the Meetup Inventor tool, that is an online tool for the development of Android applications. The application collects the data from the Arduino boards, connecting with the Arduino boards using the Bluetooth communication, and then is able to save the data on the mobile phone or mobile devices in general, but also to send the data to a database. In particular, we use the Global 5 base that respects the privacy law of the Europe. As a preliminary action to the development of the telerehabilitation service, a feasibility study was performed on 1 healthy participant. And in this case, in this feasibility study, we use a different set of sensor composed by 6 commercial Mimio sensors, in particular the Blue Trident of Icon, with a sampling rate of 500 Hz and an acquisition application that is the Capture You application of Icon. We use these commercial sensors because they are sent as sensors able to acquire motion and movements, and we want to compare these sensors with our wearable devices. The exercises protocol included strengthening exercises of both lower and upper limbs and also aerobic and breathing exercises performed in different settings, as we can see in this slide. So laying down, sitting on a chair, and also standing up. The aim of the feasibility study is to verify, first of all, if and which sensors are adequate to capture the patient's movement. But after that, it is fundamental to understand which sensor can characterize the movement in terms of quantity and intensity while the participants are performing the exercises. So we are searching for the minimum sensor setup that must be used in the IoT framework for the telerehabilitation system. In the slide, the entire system is shown, combining the prototype wearables and the commercial MIMUs in orange, and also our wearable devices. And we can see some signals, some vital signals, like for example the ECG signal, temperature and pulse oximeter signal, that are real signals directly acquired using our sensorized shirt. Data acquired by the 6-trial MIME were processed using MATLAB, and the first step naturally is the filtering operation, but after that we count the repetition number using detecting the peaks of the signals. After that also we have an intensity assessment using the correlation operation. The table here shows the results obtained in the feasibility study in detecting the correct quantity of repetitions and the correct intensity. From this table we can observe that the trunk sensors, that are the sensors we are interested in, show good results in tracking and capture respiratory and standing exercises, and they have also good potential to acquire upper limb exercises. But on the other hand, the trunk sensors have not good behavior in sensing the lower limb exercises. And in order to solve this problem, this issue, we define this final sensor setup configuration. So we have to consider the rib sensor that is fundamental for the sensing of the respiratory exercises and also the upper limb exercises. The sensor on the pelvis, and also the sensor on the ankle for the lower limb exercises. And here in the slide, also the wearable device, the wearable system develops is shown with the acquisition of some qualitative signals. In conclusion, the minimum setup has been identified to integrate and use it in the proposed wearable system. Naturally, the future developments are many. First of all, using the proposed wearable system in place of the expensive commercial sensors for the telerehabilitation protocol. And after that, naturally, the role of a larger population of elderly people or of patients that need the telerehabilitation. Also using the wearable system in clinical application. And so, thank you for your attention, and I want to thank all the team that collaborated in this study. Thank you.